And our next talk is on work done in Sanya Fiedler's lab. Sanya Fiedler is an assistant professor at the University of Toronto, and she's also director of Artificial Intelligence Lab at NVIDIA.
Hi, I'm Sanya. I am a faculty at the University of Toronto, and I also joined NVIDIA part-time last year to lead the NVIDIA Toronto AI Lab. And one of the topics we're working on is 3D content generation. So what you're going to see today is something in 3D. And this is one of the first works that's coming out of the Toronto lab. And instead of me talking, I thought the spotlight should go to the amazing student that worked on this topic. This is Sam Bankar. So he's a PhD student with me at UFT, and this was his internship work at NVIDIA. So I just asked him to next.
Hello everyone, my name is Vlad, and I'm going to present this work we call medicine. So 3D synthetic content is everywhere these days. We have amazing movies, we have amazing games, AR, VR applications like the Jim showed initially. All of this requires great 3D content and we're doing really good. Simultaneously, it's really important for AI. For example, if you take an example like self-driving cars, you really need to train in simulation, and then your simulation needs to be really, really good. This is, for example, the NVIDIA TriSim constellation. So you can see how, there you go. So you can see how we have amazing simulation. You can see, sorry, the internet's, I guess, slightly slow, but you can see that the simulation is really great. You can have different kinds of weather, you can have different cameras, the cars look amazing, it almost looks real. So this is good because this is so the problem we're trying to tackle is basically we're trying to generate synthetic data, and the issue is me as an AI researcher, whenever I get some real data set, I want to do some tasks on it. What I first say is, okay, give me something with labels and let me train something on it. And an interesting direction people are taking is generating synthetic data sets for it. But the question is, how do we generate it? But one solution is get an amazing graphics system. They're going to go and they're going to generate these things for you. So if you give them a real data set and ask them, hey, can you go and generate like a real data set, a synthetic data set that looks like what I'm generating, what I want to train on, and then I can just simulate render labels like Procedural was talking about and train on the synthetic data. This actually is really slow. So again, if this video behaves, then you can see this artist creating something that looks like this. And while this is a 24-second video, it's actually a time lapse of him working for 6 hours. So basically 6 hours of work to generate that one scene, which is basically no training data for any of the AI that we're doing right now. So obviously people have thought of solutions for this. So one solution is, can you take these real-world rules that exist? For example, you can say a road has, let's say, n number of lanes. Lanes have n number of cars. There's a sidewalk. So these rules can be encoded in what people call procedural models. And these are used extensively in games. These are used extensively for simulation, for training. And now what my graphics wizard is going to do is he's going to write down this great procedural model. And then I'm going to generate a lot of data from the procedural model and train on it. So everything looks great right now, so I can have some data set, I can train on it, and I can test on it. But it turns out this is not enough. It does not work. As we know, the field of domain adaptation is basically something that's trying to tackle this problem, and you can see that the results here are not that good. So what are the issues? So one issue is, again, what Philizzola was talking about initially, is there's a gap in the appearance. What we render is not what a real data set looks like. This, for example, is a kitty data set, but again, things look different in Japan, things look different in India, and so on, right? So one thing people have tried to do is they have tried to change the appearance of images. So you would take this image that's from some train, let's say, and then you would transform it to look like whatever target data set you want, and then you would train on it. And this does pretty good. It gives you great results. But what we hypothesize, what we say is that there's actually a bigger gap, and it's what we call a content gap. And you can clearly see that. You can see that this is the GDA5 game, the next thing is the virtual KD dataset, and they don't look like any of those images I'm showing you right there. And they don't look like that in appearance, of course, but also in content. For example, in the Indian image, there's things that we call auto rickshaws, and we have none of that in this replica of LA and so on. So you can see that there's a lot of issues in actually generating good content, right? Another important maybe application in this way is if you don't have data where you have occlusions, then you're never going to train a model that's going to do well with occlusions. And therefore, if your synthetic data in content never has good occlusions, then your trained model on the synthetic data is not going to be able to do with occlusions, and I'm going to show that in the results later. So let's go back to what we had, and let's see what we should change here to make what's happening right now much better. So we have this RAPT person, let's say, who's writing a procedural model for us, and they're thinking of some parameters here in the simulator. Some parameters such as the location of certain objects, the height of certain objects. So they're writing things like there are going to be 5 cars on the road at certain pose with a certain location in code, and then we're going to generate scenes. What we can do actually is put an algorithm in there. Let the algorithm ingest these real-world rules, take the procedural model, but then go out and say, okay, you know what, this location, this pose is not look great. Can I go change the pose of that car? Can I go change the pose of that person? Can I go move that building a little bit? Because I think that's going to make it look much more realistic. Why this is important is because now imagine your real data set is an example where you want to drive in Japan. We have no data sets right now that look like Japan. And one thing you could do is you could go get someone to write another procedural model for Japan, but then I'd say, okay, what about driving in some village in India? Then you can go write another procedural model. So you see it doesn't scale. So you really need some AI there that's going to take this procedural model, but then start moving things around, start preparing things so that things look real, right? So again, as I've always been saying, there's this notion of real-world rules and procedural models. So in our work, we define that as a probabilistic grammar, which is basically a context-free grammar which has some probabilities associated with the rules, and I'm going to get to that. So we call this algorithm medicine because ultimately what you're seeing here is you have some meta parameters for your simulation. Some meta parameters such as how many cars should be there, what should be their location, what should be their pose, what are the different attributes of these objects, what kinds of objects are there. All these meta parameters are something that we can optimize, and that's why this is called medicine. How we optimize this is we optimize some renderings of these scenes to look like some target real data set. And simultaneously, we also optimize for a model to train on what we're generating, and the optimization basically optimizes the task performance on the real data set. Again, we'll get to that. So let's dive into how we do representations in our model, and then let's see what the model looks like. So first of all, what's in a scene? So a scene, for me, and that's how we define it in the paper, is it has first a structure. For example, in this simple case, there's a scene, I'll say it has a background and a foreground. The foreground, let's say, in this example, has 2 digits. So this is an example structure of the scene. But this does not uniquely identify what the scene is, so you can see many different kinds of scenes that can be generated from this structure. So to uniquely identify the scene, you also need to add attributes to each of the nodes in the scene graph. And after that, you're going to get one unique image. So this data structure you see here is what we call scene graph, and that's something that is used more in graphics and not the vision and language kind of scene graph. So now I'm going to basically introduce more blocks that are used in medicine, and then we go into the training algorithm. So medicine has 4 modules. We saw the probabilistic grammar, the renderer, there's a distribution transformer, which is just a fancy name for the model that we're using. It's a deep network. And there's a task network, which is ultimately the performance of some model, or it is some model that we want downstream. So if I want to do some driving, then let's say one thing I want to solve is perception, and let's say detection, then a task network would be massive scale. So the probabilistic grammar, as we saw before, is basically something that you can sample a scene graph from. The renderer is what takes the scene graph and tells us what the pixels look like in that scene. So for example here, taking this, rendering it, gives me that scene. The task network is something that I care about in terms of downstream performance. So take a scene, train a model on it, and for this example, if it's classification, then you take that image and you say there's a 4 and a 2 in that image. Okay, so let's go into how we train this model. So there's actually 3 stages of training, and I'm going to go through these one by one. So first of all, reconstruction. So reconstruction is basically saying that the probabilistic grammar that you have is some prior on the kinds of scene graphs that you're generating. And what this model, the distribution transformer, should learn is to at least learn the prior. And to learn the prior, what we say is, first sample a scene graph from the probabilistic grammar. You're going to pass it through the distribution transformer, which is the model. What the model is going to do is for each node in the graph, it's going to change the attributes, like we talked about. It's going to change where the digit exists, where the car is there, what's the rotation of the car, what kind of building, and so on. So that's what the distribution transformer is going to do, and we're going to get a new scene graph. And what we're going to train it with is just a per node, per attribute reconstruction loss. So if it's a continuous attribute, you can train it with L1 loss. If it's a more class-like attribute, you can, for example, train it with cross-interval. So all good, and then you can backpropagate that with the transform scene graph. So right now, what our model has learned is basically some notion of autoencoding. It has learned how to reconstruct the prior that's given to it in the precision model. Next is the meat of what we do. It's basically what we call distribution matching. So let's go through the procedure. So you have a probabilistic model, you sample a scene graph from it, you pass it through the model, the distribution transformer, and you get a new transform scene graph. And then you render the transform scene graph, and now we start actually seeing images that are coming from what we're training. You render it and you get those images that you see right there. Now we want to basically define some notion of a loss function, some notion of the likelihood of what is the likelihood of what I've generated. So in this work, what we do is basically say that let's take the features of a big batch of scenes that we generate. Let's take the features of a big batch of real scenes, and then we compute the maximum mean discrepancy between both of them, and then we backprop them. So a quick primer on maximum mean discrepancy. So a simple case of how you would match two distributions is you would say, let's say the mean is the same. But then I could say that, oh, there's a second order difference. So you could say, okay, the variance could be the same. But then it could be a third order difference, fourth order difference, and so on. So what MMD does is it does this mean matching in kernel space. In the kernel space, you actually have all the moments defined, and you can actually show that. So if you minimize the maximum mean discrepancy, then you can prove that if two distributions, two samples, are exactly the same, then MMD is 0. And this is something you can actually optimize. So that's what we do here. And then you can backpropagate that loss into the scene graph. Now there's a catch in. There's that black box renderer, which we don't know how to differentiate right now, correct? So what we do here is we compute the gradients through the renderer using finite differences. So we have the scene graph. In the scene graph, there are many nodes. Each node has some attribute. So what you can do is you can perturb each attribute a little bit. You're going to generate a new image. And then if you do a finite difference there, you're going to get the gradient of the image with respect to that attribute. You have backpropagated the gradient of the loss with respect to the image, and you multiply those and you gradient goes back. Does that make sense? Cool. So that's the distribution matching. And finally, as I said before, we also want to optimize this notion of task performance for a downstream model. So what we do here again is the same deal. You take a probabilistic grammar, sample the scene graph, transform it through a distribution transformer, you get a new scene graph, you render it, you get a lot of generated scenes. What we do next is we actually take a downstream task network. For example, for detection, it could be SSD, natural CNN, so on. We train it on the data we generated. Since this is synthetic, the ground truth can be rendered directly, no problem. We actually train our model on that, what you can do next is, if you have some small labeled real data set, you take this trained model, test it on a real data set, see how good it's performing. That's the notion of score, and you want to maximize that score. So we do exactly that. You can compute the gradients of that score with respect to what you generated by using the reinforced trick or the log derivative trick. And that's how you can get gradients for the score with respect to each attribute in the scene graph, and you can backplot to that. This way you can do sort of a meta task of actually learning how to optimize downstream task performance while trying to generate 3D scenes. So that's great. Let's look at some results. So the first thing we tried is, like any other paper, let's do some point tests. Let's validate that this model works. So a simple point test which we generated was MNIST. So in MNIST, we said, okay, let's say we live in this weird world where our target data set is actually rotated. And the input probability grammar generates things that look like the real MNIST data set. So the distribution difference here that we want to learn is basically a rotation of 90 degrees. And then the task basically, so the classification of the task network is a small CNN, which we just designed. Here I'm showing you a video of scenes that are being transformed through time. So if you look here, you see that the scenes are slowly transforming across training, and finally we can generate exactly the same images that look like the target data set is rotated. And if you can see the next one, you can see there's a difference in the location, there's a difference in the rotation, and we can learn both of that. And if you look at the results, if you train on the rotated images and test on the real images that are straight, you're going to get near random performance. And if you train on what we generate, you're going to get more MNIST-like numbers, more things which we have seen before. So this is great, it kind of works in a toy task. Let's try it on a really complicated task. So we said, okay, can we generate 3D scenes for self-driving? And say that the task here is object detection. So we first defined a probabilistic grammar for road scenes that looks like this. You can look at the paper for more details. But we showed here that even in this very complicated scenario, we improved significantly over the probabilistic grammar. So scenes generated by our model get much better result downstream than just the probabilistic grammar itself. And additionally, what we show is if you try to bridge the appearance gap, so again, going back, we said that we're trying to bridge the content gap in data sets, right? So if you also try to do image-to-image translation on top of the images that are generated, you still see a gap between what the probabilistic grammar can do and what the medicine algorithm can do. So this is basically showing that there is actually this notion of a content gap between data sets, and that is something that you can learn. So these are some results. So on the left column, we see samples that come from the probabilistic grammar. In the middle column, these are the scenes that come from the probabilistic grammar and then are transformed by medicine. So you can see that everything now looks more realistic. Cars are aligned, there's some pedestrians brought into the scene. The houses have come closer, it's more dense, it looks more like a real data set. And just on the right, for reference, there's some random kitty images. Here you can see basically a video of how the model is changing scenes across its training. So initially, you'll see that the scenes are very arbitrary, things are thrown about. And through time, the model learns to move things around. It tries to figure out how to minimize these objectives that we have defined for it. And ultimately, it generates scenes that looks like this. And again, these are more examples. So ultimately, we said that we actually want to improve some downstream tasks. So we actually show that. So here you can see on the left, these are detections generated by a model trained on data that is created by our model, versus on the right, results in detection trained on data that is generated by a simple procedural model, which is our probabilistic grammar. So you can see that things like on the bottom right, there's a big false positive. You can see on the top left, all the cars are perfect in medicine, but if you look at the probabilistic grammar, it actually misses quite a few on the right side. And in general, as we saw in the numbers, the performance is also much better. So in conclusion, we first said that, okay, we need scalable simulation. I can't have this person sitting and generating data, simulated data from me all the time. And we said that simulators need to adapt to the diversity of the real world. And we said, okay, appearance is a difference. Appearance is being rich, but content is also a problem. And I think what we've done here is basically a baby step in this direction, and we're trying to basically solve this huge problem of generating 3D data that looks exactly like what we have in the real world. And there's lots more stuff to do. So we can actually learn structure. So if you notice in this work, the structure was all generated by this program, this procedural model that we created. But can you actually learn that? Can you actually generate these rules? Can you learn these rules from your data? And another very interesting thing for us would be, can you actually differentiably render all these scene graphs that we are doing? You need to render them fast, and then we would not have to do the numerical gradients that we were doing in the model. And there's a lot more. And there's a lot of applications. So for example, think of any simulator that you use for any kind of data set, and then you have some meta parameters that you optimize. For example, in Parla, you have parameters like what's the kind of weather, how many number of cars are there, what are the other kinds of things. And you can basically learn to optimize those parameters. Think about a medical scenario where you want to learn about what's the density of tissue in the head. And you cannot have one person giving those numbers, but you can actually learn it. And that's it. Thanks a lot.
Any questions?
About so in the afternoon we'll
Okay, well, we will be back after lunch. Follow the schedule on the website.